Okay, hope this is much better in view. Okay, so let's continue from here. Remember, before the break in the previous room, we were talking about the case of nanorobotics. We said there are two major research fields. One is design, simulation, control, and coordination of the robots, the nanorobots, and the other is actually the miniaturization process of these devices down into nanoscale. And you'd like to be able to interact with objects different dimensions at or below the micrometer range. These nanorobots are made of assemblies of nanoscale components, each in this nanoscale range. And the overall system size in total is typically limited, which brings us, this limitation on size, brings us further problems relating to actuators, sensors, the motion mechanisms, power sources, computing power, and on wireless communications also. So it affects even the communication component. Scaling the devices down, like you start with regular electronic devices, you go down to MEMS, the micro electromechanical systems, and then now down to NEMS, nano electromechanical systems. When you're taking the scale down, then the ratio between the surface and the volume increases. When an object is smaller, the ratio of its surface to the volume of the object itself is larger compared to greater objects, which implies, since there's too much surface, now those surface forces we used to ignore in the macro scale now become more effective. Actually, they become so effective that it overcomes, for example, inertial forces that result from the weight of the object, from the mass of the object, which relates to the volume. Now, since the volume is much smaller compared to the surface, now the surface forces may become more effective than the inertial forces. That's a major problem because all the physics you remember from high school, it doesn't work now. They're not effective in the scale. Now, other forces are more effective. At the nanometer scales, the interatomic forces, which compose this surface chemistry, now have a significant role. This is something we used to ignore. Like when you're calculating the power of the water to raise an object, like the ship, you never look at the surface forces. Because remember, the water has a surface force due to adhesion between the molecules. You never care about that because, yes, there is such a force, but it has almost no effect. Now, when you look at the nanoscale, it's just the inverse. Now, those forces are more effective. Inertial forces and weight, since these two are related to the volume, which is now not very important, are almost negligible. Which means all dynamics have now changed. Micro and nanoscale surface interatomic forces, fluid dynamics, the flow of the fluid, heat transfer, surface chemistry, and adhesion-based contact mechanisms and friction are now the dominating forces. So all the designs for the larger robots, they're not much useful at the nanoscale. For the nanoscale robots, it's much different from regular robotics. There are many different characteristics of these nanoscale and microscale devices. They're compared in this reference. If you're interested, you may have a look at it. But our focus is not on the robotic side in this course. Our focus is on the communication component. So my question is, okay, look at all the things we mentioned in the previous slide. like these effective forces, do they have any impact on communication? That's my question. I know these have too much impact on nanorobotics, but I'm not a nanorobotics guy. I'm a communications guy. As a communications engineer, are these new forces important in terms of communication? That's my question. And yes, actually they are. Some of them are very effective. So that's what we're looking at. As it says here, nanorobotics research is well underway. It's not our point in this course. So we're looking at communication networks that exist either entirely or mostly at the nanoscale. And the vision of nanoscale networking is now achieving the functionality and performance of today's, at least it's trying to achieve, the functionality and performance of today's internet at the smaller scale. The channels are physically separated by up to hundreds or thousands of nanometers. We'll be talking about distances of hundreds of nanometers, or mostly tens of micrometers. So that means thousands or 10,000s of nanometers, which means we're not talking about long distance communications mostly. So this is much different than all the communications you had been actually using. Look at the antennas you're using. The distance we're talking is even shorter than the antennas you have been using. The nodes are assumed to be mobile, or they should be able to, you should be able to rapidly deploy them. The nodes are assumed to be either self-powered, because it will be difficult for me to install a battery on it, and or sprinkled onto their target location in terms of deployment. Also, in addition to this self-powering, we assume that the nodes somehow do some energy scavenging. Even if you initially charge these devices, after you deploy them, they will immediately deplete all the energy they have. So how do you recharge them? You cannot recollect and recharge and redeploy. They should do energy scavenging. How you do that is an important problem. Individual nodes at such small sizes may seem to be constrained to have significant functionality. Well, actually, quite the opposite is true. Well, I should maybe rephrase this. The individual devices may not be very powerful, but they will be so large in numbers that altogether they will be able to do useful work. If you look at the body itself, it's composed of many such nano devices. The operation of the molecular motors have appeared in wide variety of contexts and with amazingly complex operation. We'll be discussing this. These molecular motors we're mentioning here are actually devices that do transportation. They're just like porters. They take a huge load named vesicle on their shoulders, and they carry them over the rails. And all this is happening inside a single cell. These molecular motors are able to carry vesicles full of many messenger molecules from the center of the cell to the cell membrane, to the border. Or even they're able to pull some organelles of the cell. And they're incredible machines, actually. Bless you. It will require communication in environments where the nodes are in motion. That might be possible. And complex dynamic environments of living organisms, or nanoscale sensors, or robots inspecting the sensitive parts in an automated process. Especially in the case of living organisms, It's a very strange environment. It's dynamically changing, and the environment itself might be attacking you. So you have to be biocompatible. If you enter a living body, you should not be harming it. If you do so, either the body will die, or in order not to die, it will kill you. So it might also be a hostile environment if you don't have a proper design. Communication should leverage the natural environment with as little disruption to the environment as possible, because you're changing the environment. Unless you really intend to do so, you should avoid it. And also in the case of living organisms, this is really arguable if you really want to change the environment or not. So the nanonetworks are basically some communication networks, but with different, in a different scale and with different characteristics, like the signal carrier wave will be different, as you will see. As such, they have the features analogous to the wireless communication networks and the internet, but they're also very different from that. The information must be somehow collected. You should acquire the information, take the information, code it, encode it, and then carry it, transport it to the destination. In the intermediate nodes, decide which way to forward it, and finally at the destination be able to receive it. But now you should be able to extract the information out of this received entity, received signal. So you should be able to decode it and deliver it finally to the appropriate application, whoever needs it. So this entails the traditional concepts we already know, but sometimes in a different manner. Like typically we're used to electromagnetic propagation. Can I use electromagnetic propagation in all nanoscale environments? Or would it be better to use it or not? We should be looking at in that. But it somehow relates to things we already know from wireless communications, or in general terms of communications, like compression, bandwidth, error correction, and network architecture. Somehow we would like to map to things we already know. The architecture includes the manner in which the data is physically realized, how it is represented, how a communication channel is constructed between the transmitter and the receiver, how do you access, how do you control the access to this channel if there are multiple transmitters? Because if they transmit at the same time, it is possible that the signals will be garbled and the receiver cannot understand anything out of it. So remember, this is what we study as MAC, medium access control. So now you have a different channel, so you have a different medium, but probably you will still need some way of controlling access to this channel. The implementation and allocation of the resources. All these should be studied. A challenging issue is not only interfacing among the nanoscale components, but also between that nanoscale and the macro scale, as we discussed earlier. It should be relayed to the higher layers, higher scales, to be useful. Otherwise, if it all remains in the nanoscale, it's not useful for the humans. The humans are extending the notion of traditional networking from both ends. Like at the larger scale, we are taking it even wider. We're taking it now to the deep space. Interstellar communications between the Earth and Mars, for example. We're looking at such scales as well as the nanoscale now. Different techniques for each scale has different results. As humans, we tend to scale from our own anthropomorphic perspective. So anything from the scale of Mount Everest down to the size of a bacterium can be considered as human scale. These are the things, these are the scales at which humans operate. Anything larger than the Mount Everest, this is, well, a little bit beyond this Earth, so it turns into astronomical scale. Anything below that bacterium scale is now going into such a small scale that it goes now inside the cell. So we will call that the cellular scale. Because this is the size of a cell approximately. Note that the size of a cell widely varies. Most of the cells we'll be discussing will have a diameter around 10 micrometers. But there are cells that are as large as, for example, the neurons at the neck of a giraffe grows more than a meter. It's around 2 meters in length, not in all dimensions. But the size of the cell varies. But what we will consider will be typically, as I said, around 10 micrometer scale. So that's why we call the scale the cellular scale. And from 10 to the minus 9 down to 10 to the minus 15, this is the size of the protons and the neutrons. It's called the atomic scale. And finally, below that, we'll call the subatomic scale. So it's no coincidence that the nanometer is at the cellular scale. And many nanonetworking approaches attempt to leverage what is already being done in the nature, understand from the nature, and go in a bio-inspired manner, as we'll be discussing. One important thing we should realize is actually we're not creating new things. We're actually observing what's going on in the nature. And from that, we learn and we try to control the nature. And we try to have, we would like to repeat the natural phenomenon in a controlled manner so that we can benefit from that. Like, we didn't invent the electromagnetic waves. The electromagnetic waves were there since the beginning of the whole universe. We just realized that there is something as the electromagnetic wave. Realizing that was a very important step, but it was not useful for us until we found the way to control it. Now, once I find how to control the electromagnetic waves, I'm able to send a signal from this microphone to the earphone Tugcu is supposed to have in his ear to check if the microphone is still working or not. So once you can control it, it's useful. Okay? So that's what actually we're trying to do at the moment. I know that in the nature there is something going on in the nanoscale, but it's not under my control at the moment. Can I control it? So this is explaining that. That's a very nice example. The flagellum, which is in the flagellar bacteria, is actually a piece that is of the size 13 nanometers and with a length of 50 nanometers. And this thing is turning. Flagellar bacteria is able to turn it. And this works like a propeller. This way, the bacteria is able to move using this propeller. This is really a motor. This is just like the motor you have at the back of the boat. One minor problem. I cannot control where the bacteria is going. It just goes in a direction. When you look at the movement of the flagellar bacteria, it just goes this way, then it stops because the flagellum turns in one direction for some time, then it has to rewind. So at that moment we say it's tumbling, and then it makes another movement in another direction. This way, this way, this way. It's making strange movements. The problem is I'm not able to control it. If I can control it, if I could tell the bacteria to go in one direction, that would be perfect. Or maybe I don't need to control it. Maybe if I have enough of those bacteria, and if I can put my information, if I can piggyback my information on the bacteria, one goes that way, the other one goes that way, but some of them go into the direction I want. In that case, well, my information will be transported. Some of the information will be sent to wrong addresses maybe, so hopefully they should be discarded. And I should also care about the energy efficiency of the system, because I have spent some of the energy of the system for the wrong purposes. They went to the wrong places. But look at how much energy I have spent in total, and how much energy, how much information I was able to transport finally. So from that you can find the energy consumed per bit. If it's reasonable, then this is a reasonable way of communication. If not, it's not. By the way, you might have heard recently heard on the newspapers that they were able to control the movement of the cockroaches. Okay, the cockroach is not in the nanoscale, unfortunately. They're huge and you see them and they're not nice animals. But it's important that you could direct them. They've been able to direct them. That's a significant improvement. So at what point our understanding allows us to transform these natural phenomena into nanoscale communications or networking as an engineering solution? That's the important question. Okay. As I said, nanoscale transportation is already being used at the cellular level. This way our bodies are still alive. But this is not engineered. You cannot tell one of your cells to send a signal to the other cell. It's just going on in your body, but unfortunately you're not able to control it. If you could, of course, that would probably improve your body significantly. When engineered information flow can be sent and retrieved and routed at the cellular level with full control at the human level, that's where we have the nanoscale networking using molecular communications. Definition of the nanonetworks will be shaped by the forces that are deriving this development and the techniques for this purpose. There is a strong convergence from the human scale to the cellular and atomic scale, as we discussed. And somehow these systems have very good relationship with the sensors. The sensor networks we already discussed. You can look at the non-invasive and minimally invasive sensing methods. Sensors inside the body should be small, because we do not like having a huge sensor like a cell phone inside your body. So they should be pretty small so that they will not disrupt the organ functions. And inspection equipment must be able to fit inside small crevices to be able to detect what's going on inside such small places. Okay, I will just skip this slide. Early advances in sensing has also helped the nanoscale sensors, like the biological and chemical sensors we discussed earlier. And these have close relationship with nanotechnology. Actually, there are sensors that make use of the nanotechnology for the sensing component itself. On the other side, quantum networking is growing with a rapid pace. The systems biology has been both a driver and also an early enabler for nanonetworking. One thing you need to notice at this point is the following. The biology world has already knows most of the things we're discussing. There's a minor problem. We have no idea about what they know. As engineers have been isolated from the biology world for a very long time, except for biomedical, but they never went down to cellular level. Somehow, these guys in the biology world, they know how these things are working, how the cells are working, but they don't have the communications perspective. We have the communications perspective, but we have no idea how the cells are working. If you can set up a proper relationship with people in the biology world, you can do great things. That's actually what we're doing here at Boğaziçi University. We have, for example, a partner from Istanbul University Biophysics Department, Dr. Bilge Özarman Edis. We have close relationships with her, and we have published several papers with her, and we still have ongoing work together. She knows how the cell is working. Remember we said actually the nature, the human body and all living bodies are working, making use of nanoscale communications. She knows how it's working, but she doesn't know how to make use of it for transporting information. I know how to do communications, but I don't know how the cell is actually doing it. Together, we've made a good couple, and with Birkan and Tugcu, we've been doing some work, and now also with Gaye and Ali, we're going a distance. The important thing is you should find such a partner, because this thing has to be interdisciplinary work. We cannot attack this alone without the support from the biology world. Experimentation, validation in systems biology also requires information from very small sensors. Source and channel coding are very important for cryptography, but that induces some computational overhead, which rapidly grows with the scale. The limiting processing can be packed into smaller volumes with these technologies. And given this limitation, more of the computation should be done by the non-traditional methods. For example, you may shift some of the cryptographic processing to the network side by making use of the network topology as part of the computation. There are ways of doing this. What's the caveat in all this? Somehow there should always be money in it, which means the industry. The industry is actually reaching the limits when we look at the processing speeds of the processors. They've come down to several tens of nanometers, and somehow you need a significant leap in technology. You can make it smaller and smaller and smaller, but up to some point. At some point, you have to change the paradigm so that you can make a significant jump. Like the invention of the transistor was a significant change in the paradigm, which provided a significant jump in electronics technology. We need something similar now. We have to change the paradigm to achieve this. At the moment, industry is stuck, almost, not exactly, but it's going towards the limit. They're running towards the wall, and they're almost stuck with the size, because you have the power consumption problems, current leakage, and heat dissipation. As things are getting smaller and smaller inside the integrated circuits, these are the three problems they're encountering, which motivates the research towards different technologies. One is network on chip, another one is system on chip, which is actually the integration of an entire system onto a single chip as a macroscopic device. The current lithography-based approaches will continue to evolve, but up to some point. At the longer term, at the scale of 22 nanometers and less, you have the main challenges. It's difficult to go beyond those limits. Like in the next, actually by the end of this decade, we're expected to approach the 10 nanometer boundary. We're getting stuck there. There are some novel ideas for fabricating computing devices, like combining. Now this relates to your question in the first half of the course, of the lecture. Self-assembled DNA structures with the other elements like carbon nanotubes. Carbon nanotubes are typically you may consider them like electronic devices. These are carbon based systems, as you will see soon. But if you can put them together with self-assembled DNA structures which can reproduce and modify themselves, if they can work together, that would be great. And actually, there's some research going on towards that direction. Currently, we're around the 32 nanometer scale in the lithographic techniques. And as I said, the industry is expecting to reach around 10 nanometers by the end of the decade, which creates significant concerns about the production processes. How do you produce devices at such a small scale with the current technology in mass quantity? Pay attention. They're very small systems built in the labs. That's possible. The important thing is you should be able to mass produce them, and in a cheap manner, so that we can sell it to the people. Having something in the lab is a great step. It's a very important step. It shows that something is doable, but you have to find ways of mass producing them. Otherwise, a single chip will cost thousands of dollars, which will imply that the notebook or the cellular phone you need to buy is now tens of thousands of dollars, which nobody will buy. Okay, so you have to find a way of mass producing them in a cheap manner. Researchers are currently therefore looking at other approaches, like making use of carbon nanotubes to achieve this objective. And this is the basis of considering the long-term approaches for these DNAs and carbon nanotubes together, because they need it. So what the heck is this carbon nanotube? The carbon nanotube is, before the carbon nanotube, we should understand first the carbon nanoribbons, because you take the ribbon and from the ribbon you form the tube. And this is formed by using something called graphene. This is actually a sequence of carbon atoms arranged in a specific manner. They're perfectly aligned to form a ribbon, okay, which is just a flat rectangular structure, you can think of it that way, which is composed solely of carbon atoms, nothing else, in a very regular layout of the carbon atoms. Okay? It's just like a long sheet of paper. Okay? I wish I had some paper with me. Can I have a single sheet of paper? Sorry. Like this. Okay. Now from this ribbon, okay, it was very thin, so you can form a tube. A more regular shape, of course, than I did. Okay. And this becomes now, the first one was a carbon nanoribbon, and from the carbon nanotube, what I did was actually bring the two ends together. And if I form the bonds between the carbon atoms on this side and this side in a proper manner, this will be a tube. Strange enough, such a tube could be bended, but it is one of the strongest materials on Earth. You cannot break it. Also, how do you form the ribbon? I just folded it this way. I just folded it this way. What if I fold it like this, with an angle? Okay, sorry, I'm not good in origami, I should say. What if I do it folded? The electrical conductivity of such a tube is different from a tube which does not have that angle. I can play around with that. Okay? So I can make that either a conductor or a semiconductor, for example. But as I said, it's a very, very strong structure. That's very important. You can make it very long, but still it will be very strong. Sorry for messing up with the paper. The atomic structure of the carbon nanotubes make them mechanically strong, as I mentioned, and the atomic properties lead them to be conductors or semiconductors, depending on how you fold them. The carbon nanotubes have been used to construct electronics, like resistors, capacitors, inductors, diodes, and transistors, as of today. So it's something like this. It's a tube like this. Okay? Each red dot here is a carbon atom, and the yellow lines are showing the bonds between the carbon atoms. So these are rolled tubes of graphite with balls constructed from hexagonal carbon rings, and they can be formed into large bundles, just like the electronic wires all bundled together. Now, one of them, what you see in the previous figure, would be a single wall nanotube, because you have a single wall, or you could have many of them, one inside the other. In that case, it would be a multi-walled nanotube. You can take this and attach what we call a buckyball onto this, again from carbon atoms. This is just like a ball attached to a part of it, which could be used for holding the carbon nanotube. Okay. Now, if you push that ball altogether, the tube will go forward or backward. It will work like a handle on the carbon nanotube. There are various ways of making use of them. Due to their small size, the carbon nanotubes can reach deep into the environment without affecting their natural behavior. Actually, a single carbon nanotube is small enough to penetrate through the cell membrane. If you normally try to do it with something else, the defensive mechanisms inside the cell will try to fight against this. And if not, it will kill the cell. Okay? But in the case of a single carbon nanotube being inserted through the cell membrane, it can work without triggering this self-defense mechanism of the cell. Okay? That's very important. Yet, there are some researchers saying that carbon nanotubes are biocompatible because they don't have, for example, they can work without triggering the cell defensive responses, whereas others argue that carbon nanotubes may cause cancer. So that's still arguable. That side is still arguable, which is beyond my information, so I don't want to comment on that any further, but I just want to say that there are some health concerns being discussed at the moment, as far as I know, not finalized yet. The individual nanotubes can be used to construct a network of sensing elements, and the depth and the coverage provided by such a network of sensing elements is greater than today's sensor networks. The important thing about the carbon nanotubes is they're in the nanoscale. Again, they can go into the smallest place you wish to use, different from the regular sensors we already know. From a medical standpoint of view, the use of wireless implants using the current techniques is not acceptable for several reasons. Yes, in NetLab we are talking about having sensors for health, but those are over the body, not inside the body. They are not intrusive techniques. With Geometry, we're not discussing having wireless, sensor nodes, wireless sensor nodes embedded inside the body, communicating using wireless technologies. That's not what we're using there. What we have there is larger sensor nodes that are attached to the body. For example, for getting the body temperature or the heartbeat or whatever information you can get from outside. That's different from what we're discussing here. The reason they're not acceptable inside the body is they're bulky. You don't want to have large such devices inside your body. You cannot use magnetic resonance imaging if you have something like that in your body. Well, you probably have something like that in your body because you have some health problems. Then due to your health problems, you want to have MR, but they say, no, you cannot have it because you have this device. So it's just conflicting with your health needs. Potential radiation damage and surgical invasiveness. You need to recharge them and to place the power as necessary. There are, for example, insulin pumps that are partly inside the body, but partly outside because you have to recharge them, both with insulin and also for power. The post-operative pain for having this placed inside your body and long recovery from such operations. And the reduced quality of life for the patient, because if you're carrying let's say insulin pump, then you're not able to do sports. This is very important, especially for the kids, for example. So it also affects the quality of your life. If you can do something that would work in the nanoscale, then it wouldn't be visible and you wouldn't feel it in your daily life. The development of both biological and engineered nanomachines is progressing as well. Such machines will also need to communicate. That's why we are having this course. The networking among these sensor devices and also among the robots using traditional techniques like wireless technologies is not possible without the communication mechanisms exceeding the nanoscale. Yeah, if you have such devices, then your communication components should also be large, not at the nanoscale. Randomly aligned nanotubes may be considered, and biological approaches should also be studied. That's actually my research focus. Sensor coverage will also benefit for finding better ways of communication. You need low-cost, robust, and reliable communication among these machines, and communication with these newly engineered inorganic biological nanosystems will allow us to have extremely dense and efficiently distributed operation.